We won't use the definition of instantaneous velocity too much in this course, but I want you to at least understand the concept of instantaneous velocity is the velocity at a moment in time. For example, let's say a car travels at a constant velocity of 40 kilometers per hour. At point 1 hour, the instantaneous velocity reads on the odometer 40 kilometers per hour. At point 3 hour, the instantaneous velocity is still 40 kilometers per hour. It would happen to be that this example has instantaneous and average velocity equaling to 40 kilometers per hour. In the next example, the car is varying its velocity. At point 2 hour, the instantaneous velocity happens to equal the average velocity of 30 kilometers per hour. However, at point 1 hour, the instantaneous velocity is instead 50 kilometers per hour, where the average velocity is still 30 kilometers per hour. At point 4 hour, the instantaneous velocity is 20 kilometers per hour. And at point 5 hour, the instantaneous velocity is 0 kilometers per hour, but the average velocity always remains 30 kilometers per hour. Exercise B. What is your instantaneous speed at the instant you turn around to move in the opposite direction? It's always 0, because when you turn around, you must come to a complete stop, even if it's for an instant before moving in the other direction. The next concept to understand is acceleration. The definition of acceleration is a change of velocity over the change of time. Mathematically, we can represent acceleration by delta v over delta t. Please note that the initial time for pretty much all problems we deal with in this course will be 0. In the example, we have a car starting from rest and quickly accelerating to 75 kilometers per hour in 5 seconds. How do you solve for the acceleration of the car? Excellent start. By applying the equation, you get 15 kilometers per hour second. However, the units are a little funky. You can change this answer to units of meters per second squared. To do so, we use unit conversion to change hours into seconds and kilometers to meters. To check and see if you set up the conversion correctly, all undesired units should cancel out. After plugging and chugging, you should get 250 meters per second squared. The SI unit for acceleration is meters per second squared. The previous example showed positive acceleration. Can you solve for the acceleration in this example below? Yes, you're correct again. By applying the equation, you should get a negative answer. Please be aware that there is a difference between negative acceleration and deceleration. Negative acceleration only depends on how you set up the coordinate system, and deceleration refers to the object slowing down. Slowing down occurs when acceleration is in the opposite direction of velocity. Let's do this example again, but a little bit slower. An automobile is moving to the right along a straight highway, which we choose to be the positive x-axis as seen above. Then the driver steps on the brakes. If the initial velocity when the driver hits the brake is 15 meters per second and it takes 5 seconds to slow down to 5 meters per second, what is the car's average acceleration? First step, write down the definition of acceleration, change of velocity over change in time, which equals to the final velocity minus initial velocity over the final time minus the initial time. So therefore we get 5 meters per second minus 15 meters per second over 5 seconds minus 0. Plug and chug, and we get negative 10 meters per second over 5 seconds, which equals negative 2 meters per second squared. The negative refers to the acceleration pointing in the negative direction. Since velocity is pointing in the positive direction, the car is slowing down because the velocity and acceleration are pointing in opposite directions. Now the car is moving to the left and slowing down as seen above. What is the acceleration? Again, start with the same equation, change of velocity over change in time. The final velocity is negative 5 meters per second, minus the initial velocity, which is negative 15 meters per second, all divided by the change in time, which is 5 seconds. Two negatives equals a positive, and so we plug and chug to get 10 meters per second over 5 seconds, which we know equals 2 meters per second squared. Now the acceleration is pointing in the positive direction, but since velocity is in the negative direction, the car is slowing down because the two vectors are pointing in the opposite direction. Exercise C. A car moves along the x-axis. What is the sign of the car's acceleration if it's moving in the positive x direction with increasing speed? The acceleration must be in the same direction as velocity or the car's movement, so the acceleration is pointing in the positive direction. Now for decreasing speed, the acceleration must point in the negative direction so that the velocity and acceleration are pointing in opposite direction for decreasing speed. Now, what is the sign of the acceleration if the car is moving in the negative x direction? With increasing speed, the acceleration must also point in the negative direction, the same direction as movement or the same direction as velocity. So two vectors pointing in the negative direction will cause increasing speed. And then for decreasing speed, that's right, the positive direction. So the velocity is pointing in the negative direction, acceleration is pointing in the positive direction. Two opposite direction means decreasing speed. Lastly, I want to briefly touch on instantaneous acceleration. Just like instantaneous velocity, instantaneous acceleration occurs only at a moment in time, as shown by the yellow stars below.